Who Planted These Nails in This Wetland Soil? A video presentation on redoximorphic features in soil by Jessica Connor, Agricultural and Environmental Engineering,
Ben Tharrington, Ecological Engineering,
and Richard Wright, Environmental Engineering.
In this presentation, we will first take a look at what a redoximorphic feature is and some of the terms used to describe this phenomenon. We will then discuss the chemistry behind redoximorphication and what the physical features of it are, and then end the presentation by talking through the uses and applications of these redoximorphic features. This picture gives us an example of redoximorphic features, which are the redox concentrations, the redox depletions, and the redox matrix that we will discuss throughout this video. Some of the terms we will be using throughout this presentation: iron in redoximorphic reactions. The presence of iron 3+ and iron 2+ are what clue us in to where reactions have taken place in the soil. Redox is short for reduction oxidation, a reaction in which certain elements lose electrons and are thus oxidized, while other elements gain electrons and are thus reduced. Redoximorphic features are a result of the natural breakdown of iron due to the presence of water and results in the depletion or accumulation of iron ions. Redox concentrations result from an accumulation of iron oxides. Redox depletions result from a depletion of iron oxides. Reduced matrix is the low chroma matrix that changes color when exposed to air. This picture shows areas of iron concentrations and iron depletions.
Aerobic respiration takes place in the presence of oxygen, which is the universally preferred electron acceptor due to its high electronegativity. Anaerobic respiration takes place in the absence of oxygen. Without oxygen, bacteria rely on a variety of other elements such as nitrogen, manganese, and iron to serve as electron acceptors in their respiratory processes. In an unsaturated wetland, the soil exists in an aerobic condition as seen in the first picture. Following a rain event which causes the water table to rise, the wetland turns to an anaerobic condition. In the absence of oxygen, nitrate, and manganese 2 oxide, iron 3+ becomes the electron acceptor. Iron 3+ is reduced to iron 2+ along the plant roots where the bacteria live. Iron 2+ is water soluble and therefore is washed out of the soil when the water recedes. As water flushes from the soil is returned back to its original aerobic condition. Any iron 2+ that didn't get washed out with the water is reoxidized to iron 3+. This process lowers the overall iron levels in the soil. Oxidation is the reaction that results in the production of electrons. In this case, oxidation occurs when bacteria in the soil break down organic matter or any other compounds that contain carbon. These electrons are then given to the iron 3+ in the reduction reaction. In this anaerobic respiratory scheme, organic matter is the electron donor, and iron 3+ serves as the electron acceptor. Byproducts of the oxidized organic matter are carbon dioxide, water, bisulfide, ammonia, and phosphate. The byproduct of the reduced iron 3+ is iron 2+.
Since reduction is an anaerobic process, oxygen is not the electron acceptor. Iron becomes the electron acceptor and oxygen becomes the electron donor. In iron oxide, iron has a charge of 3+. Iron 3+ coats the outside of the soil and gives it its red color. The oxygen grabs the hydrogen atoms to form strong hydrogen bonds. Iron, now separated from the oxygens, needs electrons to form an octet and become as stable as possible. Iron grabs the electrons produced in the oxidation reaction and becomes iron 2+. Iron 2+ is soluble in water and washes away from the soil with groundwater, leaving the gray color of the soil behind. Red soils contain iron 3+ and show a lack of water in the soil. Gray soils are a result of iron being removed from the soil by water, and thus indicate that the iron 3+ has been converted to iron 2+. These features can be vertical columns, typically caused by roots, or horizontal plains, typically caused by flooding and drainage. Studying redoximorphic features shows where water has been present and helps predict future floodplains and water tables. Gray iron-rich soils indicate that the soil has poor drainage, an important factor to consider for land development practices, such as installing a septic system. Redoximorphic soil features also have agricultural implications as well. They indicate the drainage of the soil, as well as how aerated or saturated the soils tend to be. Gray soils can also indicate high iron concentrations in the groundwater supplies, as the soil color means that the iron has washed out of the soil. If you'd like to find out more about redoximorphic features, Here are the resources we used in this presentation. Thank you for watching.